Okay, so we're jumping right back in. In the last lecture, we covered diffusion and osmosis. We really talked about osmosis. And then now what we're going to do is we're just going to apply what we learned about osmosis to both plant and animal cells. So in this slide, we're talking about cells that lack a cell wall. So that's why it says water balance of cells without walls. We take into consideration what you learned about osmosis in the last lecture, and now I can talk to you about something called tonicity. So a formal definition for this word is it's the state of a solution in respect to osmotic pressure. And a simpler way for me to put that is we're looking at the ability of a solution outside of a cell to make water move into or out of the cell by moving just water and not the solute. So why doesn't the solute move? And the answer to that would be because the plasma membrane is selectively permeable, as we've already stated. So the solution may be, or excuse me, the solute could be too big, or maybe the cell membrane could be lacking a protein channel to help move this solute through. So instead what we get is the movement of water, which would be osmosis. So there are three possible states that exist, and we have a term that we use for each. One of them is isotonic. Something can be described as hypertonic, like the solution can be described as hypertonic, or hypotonic. So isotonic solutions, they're ones in which the solute concentration is the same in the cell and outside the cell. So in that situation, we get no net movement. And then in hypertonic solutions, those are the ones in which the solute concentration is greater outside the cell than inside the cell. So when I hear hyper, I think about someone being filled with sugar or caffeine, and this helps me remember that a hypertonic solution has a lot of solute. So in this case, water would leave the cell in an attempt to balance out the solute levels outside of the cell, which would cause the cell to shrink. And then finally, hypotonic solutions, they're going to have less solute present outside of the cell. So water would want to move into the cell to try to balance out the solute levels in the cell. And all three of them that I just listed, isotonic, solute concentration is the same, in and out, no net water movement. Hypertonic, solute concentration is greater than that of the inside of the cell, so we lose water. And then hypotonic, less solute than inside, the cell's going to gain water. So figure 5.11a is showing us the water balance of, they look like red blood cells. I'm going to go with yes, they are red blood cells. So in the first one, here's your hypotonic solution. Because there is water rushing into the cell, we risk the risk of rupturing the cell. So they say that the cell can lyse or has become lysed once it's ruptured. Isotonic solution is what we're aiming for in a red blood cell. So you want the net movement of water to be 0, but again, it's consistently flowing in and going out. And this is what the goal is. That's what you want when you're hydrating, when you're eating. That's what you're trying to achieve. All right, and then here in the last one, here's your hypertonic solution. So because there's so much solute outside, the water that is inside of the red blood cell has a desire to leave to go and fix the solute issue outside. And what happens is the cell shrivels up. So when a cell is in a hypotonic or a hypertonic environment, there's an automatic reaction that happens, and it's called osmoregularity. So this helps keep things in balance. There's an example given in the last bullet point right here. You can pause it to read it. All right, then here's a picture of the contractile vacuole of a paramecium, which they talked about in the last bullet point of the previous slide. So it's just a visual to go along with the description. Now we're going to turn our attention to cells that have a cell wall, so plant cells. One of the functions of the cell wall is laid out in the first bullet point, and that is that cell walls help maintain water balance. When the environment is hypotonic, water rushes into the cell until the cell can't take anymore. This helps plant cells plump up, and we refer to these firm cells as being turgid. When the amount of water inside the plant cell is equal to the amount of water in the surroundings, the plant cell becomes flaccid. So that's your isotonic situation. Plants don't like it, but it's what we want to achieve with our red blood cells. So when you have the isotonic situation happening with plant cells, you're going to see the plant start to droop. So that would be a good time to give it some water to help it become turgid again. So if the plant cell is given a salt water solution, or I don't know, let's say the plant is outside and there's some runoff that goes into the ground and it creates this hypertonic situation where there's a lot of solute outside, water is going to leave the plant, and when that happens, you get a shriveled up plant cell. So they call this plasmolysis. All right, figure 5.11b. So now this is like the other part of the red blood cells that we were just looking at. So in this case, you see the plant cell is turgid, it's happy when things are hypotonic, right? And for us, that wasn't the case. Our cells were going to lyse or rupture or burst when that happened. Yep. Come on in. Come here. Say hi.
Hi.
My name is... Wow.
My name is Daryl.
Okay, bye, Daryl. No, goodbye, Daryl. Goodbye, Daryl. Okay, that was my son. Interruption. Okay, so yeah, hypotonic there. The center one is flaccid, so that's your isotonic situation. This is not okay for a plant, perfect for us. So you see that our cells require different amounts of water. And then finally, you have the hypertonic situation. None of us like that, plant nor animal. It's bad for both. So that's it. I'm done. Picking back up with facilitated diffusion in the next one. Goodbye.